So we're here to talk about something that we're working on in the context of Develocity, but I promise this is not a product talk. This is really about the nuts and bolts of what we've done. I will talk a little bit about why we're doing it and where we're going with it, but it is not a product talk. Okay, so I'll kick things off and then I'll hand over to Justin to talk about the nuts and bolts. All right, so the title of the talk is Automating Build Failure Analysis, but what do we actually mean by that? What are we automating and why would you do that? So if you think about what happens when you're confronted with some kind of failure, build a test failure in various different contexts, as a human or as an expert, what is that analysis process? What is involved in that? So you're trying to extract some kind of meaning, take some kind of action, probably remediate the failure in some way. What are you actually doing? What are we trying to automate? Well, after thinking about this a little bit and talking to people about it, the model that we came to is something like this. So as humans and people experienced with this kind of task, we get pretty good at looking for certain keywords in, you've got some kind of failure log in front of you. Sometimes that can be a massive wall of undecipherable text. But you, over time, train yourself pretty well to scan that and pick up on key bits of signal within that. Gathering context. So the other thing we're often doing in analyzing a failure is trying to pick up other context around this failure, such as or part of the code base does it relate to? Is it potentially related to some other initiative going on, or some tool is being changed, or something like that? You're basically picking up context about this to try and solve it. Another very common task is identifying if there is any relationship between this failure instance and any other failure instance. So that can be as simple as, well, has this happened before? Or did this happen at the same time as 40 other failures, and therefore there's probably some kind of relationship towards that? So these are things that we're, as software engineers and people working this, are just intuitively doing as we go through this. And of course, ultimately, looking for some kind of path or some kind of indication of what is the root cause, where do I need to go to fix this? So this is what we think about in terms of analysis of build failure. And one of the other things that we identified, and from our own experience and talking to customers and users, is that if you have a certain degree of expertise in the system that you're working with, this process is dramatically more efficient and effective. So we're really relying on a lot of sort of intrinsic knowledge when we go through this process. And the problem with that is, of course, is that that's a difficult thing to scale. Expertise is difficult to scale. So when we think about the problem in those terms, what we tried to think about is, okay, well, is there a way that we can automate some of this, or at least make this more efficient in some sense? So that's what we're trying to do. But why? Well, obvious one is faster troubleshooting. Reducing mean time to resolution is a key thing we're all trying to do. So by pulling more context into a failure situation, or making the context more explicit, so we're relying less on that intuitive inference to do that, in a lot of cases will lead to faster resolution. A big part of what we're doing, as I mentioned before, is that scanning process. Going through that failure information, extracting the key bits of signal from all of that noise that we're then going to make decisions on. So what is the important information here? What do I really need to pay attention to? Where do I need to dig in? And another thing that we're looking at as part of this is, okay, is there room for associating a particular failure or something that's just happened with known problems and known fixes, or even potential fixes? So by automating some of this analysis, can I detect that, okay, this is actually similar to a problem that we solved last week. How was that problem solved? Can I suggest that to a user at that point? The last time this happened, the person who fixed it did this. Maybe that's a relevant thing to do right now. And so that's looking at, I'm trying to solve a problem right in front of me. Very important task, but there is more to the story than that. So another very common reoccurring theme that we have seen talking to people dealing with any kind of central build infrastructure is getting a picture of what is happening at scale is really difficult. So the data that we have, or the picture that we have about, what are the most impactful failures? Are we actually fixing them? What is really going on at any point in time is difficult. So by introducing automation that extracts more meaning or brings more information forward and does all kinds of other sort of linkages to information, if we can reduce the toil required to to curate the data in some sense to get a more accurate picture of what is going on, well, what does that give you? Well, data-driven prioritization is another big one. And a common problem that we see is that the root cause of a problem, or the actual the problem itself, is hard to quantify because of many different manifestations or presentation of the problem. So just in being able to understand that, okay, well, this is one class of problem to be fixed is difficult. And so reducing the toil and being able to make those linkages is going to make a big difference. And once you have that better information, being able to trend and track different types of failures becomes a different situation. And also just for digging in for mining and research, understanding, okay, what are the faulty parts, which tools are causing the problems, this kind of thing. So really by improving the quality of the data, by automating some of the analysis on it and curation, what does that unlock? So that's why we're doing it. I'll talk a little bit more about the product aspect of that at the end. At this point, I'll hand over to Justin.
Yeah, so this is sort of the problem space that the data science team jumped into. And before I talk about exactly how we're approaching the problem now, I think it's helpful to understand how we approached the problem in the beginning and why those early approaches didn't work. So right from the beginning, our first thing was let's try and approach classification and clustering of failures in the simplest way possible. And we did that through a combination of metrics and heuristics based on domain expertise. It was pretty obvious right away that this wasn't going to work. There are too many different types of failures where no matter how many different types of metrics you collect, there's just no way to adequately describe any type of problem that's occurring. It was quickly pretty obvious that text data is king. And I think intuitively that makes a lot of sense when you're looking through a failure that you don't understand. The first thing that you're going to do probably is you're going to look at the exception messages, you're going to look at the logs, you're going to scan for the relevant information, right? And that data is very, very rich. It's very easy to describe what is going on very efficiently through text. The problem is that it's very, very messy and can be difficult for computers to understand. So how do we take all of this text data that we get for a failure, turn it into something that we can reasonably represent through data, and then use that to sort of tackle all these problems that Luke discussed earlier. So we started with the basics, right? We always want to start as basic as possible and sort of work our way up in the complexity chain. So we started with, the classical NLP-based approaches. I won't go into too many specifics because this is a lightning talk, but I'll say this. A lot of those approaches, those early approaches to NLP problems are based on the words that appear in a piece of text and how many times those words occur. And sometimes we'll take into account things like these words appeared in this piece of text, but in general don't appear as much, and yada, yada, yada. You can get better results this way, and in some cases you can get pretty good results. But again, there were too many times in which, when you compared a failure message in this manner, there were too many times in which the results didn't make sense or they weren't very useful. And I'll provide a few examples of that to sort of make it concrete. So comparing the text pieces on the left to the text pieces on the right, just look at the first row, and you can see node failed with an exit code of 1 and node failed with an exit code of 127. Structurally, those are almost identical, right? They've got almost the exact same words. The only thing that's different is the exit code. And if you're just looking at words and counts and applying those sort of simple methods, you're going to get a very, very high similarity score. But you, as experts in software engineering, it's pretty easy to tell that these are talking about very different things. And all of these examples sort of show that, right? For the second row, every single word is identical. The only difference is the ordering, but it means something very different, right? Server cannot connect to client is very different than client cannot connect to server. And there are plenty of other examples of this. I'm sure you can think of even more examples than are what are up here. So, I got to talk quicker. So this is where we ended up at. We know that text contains the information that we want. It's very rich, but it's very messy and it's complex. And in a lot of cases, in our context, it relies on sort of some domain expertise. So how do we tackle that? Semantic embeddings for failures. That's what we landed on. There are a lot of very, very good, very interesting encoder models out there now. I'm sure you've heard a bit about all these large language models that are popping up, and a lot of them deal with taking input and outputting human readable information. But there's a subclass of those models called encoders, right? And what they do is they take text input and turn it into a vector of numbers called an embedding. And that embedding is exactly what we're looking for. It's a rich representation of the meaning of a piece of text. And a lot of them, if you're using these pre-trained open source models, a lot of them will be good for general use tasks. But what we wanted to do was take one of those and fine tune it to our domain, right? So let's make it really good at comparing text within. I gotta talk faster. Text within the context of failure analytics, right? And in particular, we want those vectors to represent the action and the fault that's within a piece of text. So what does this look like on real data? Again, we have, at the top, two pieces of text that look very, very similar. They mean something very different. We should be able to calculate the similarity between those two pieces of text and get something sort of middling, as opposed to, if we have good vector embeddings, take a piece of text that looks completely different structurally but is representing the same thing and get a score that's much, much higher. And if we can do that, there's a lot of power in how that can be sort of used and applied in sort of a broad scale. You can use these sort of atomic embedding pieces, aggregate them together, and, for example, categorize failures into predefined groups. You can find groups of related failures. You can, allow users to say, hey, I want all of the test failures that are related to, that were caused by this specific thing, and sort of write that out in just human text and be able to pull back related build failures from a vector database. You can get much, much deeper test failure analytics from that. And even you can build off of that to do root cause analysis. If you have this sort of mathematical way to define groups of failures that were caused by the same thing, you can then compare that to the builds that happened after that were resolved. And all of a sudden, you sort of have a much more dynamic and useful way to tackle root cause analysis. I had an example of how to use this on real data that we're going to skip because I'm almost out of time. But if you'd like to see it, come see me after. The key thing to take away from this is that, if we can break up a real failure into these chunks, it's very easy to train a classifier to filter out the crap, the stuff that we don't care about from the console log. Keep a vector embedding of what we do care about, and then search through those embeddings to find, find failures that have a particular type of signal that we're looking for. We can find related groups on CI in the past 3 days or something like that. And those vectors also make very, very good input features into a classifier, so you can sort of define these useful predefined groups as well, and sort of using those as the input to the model. How much time do I have? Okay. It can be tricky, though, because, like I said, text is messy. And these models do a much better job of handling for text data and the sort of pitfalls that can come out of that, but it's not perfect, and you have to be careful. These models, as smart as they claim to be, they are kind of dumb, and they do cheat, and you have to watch out for that. For example, you might have a particular exception class that's related to that is related to like timeout failures, most often, for example. But then maybe you have a snippet of code that's related to like a compilation error, and it's from a method that throws a timeout exception or something like that. You want to make sure there's a lot of different cases like that where like if your model is overgeneralizing, it's just going to assume that's related to a timeout exception, but in reality, it's just a piece of code, right? I've seen all kinds of goofy stuff. I've looked at a lot of console log texts. I've seen some where it's like printing out an error that's very specific, and then there's like an arrow, and it says, this isn't actually a problem. So you never know what you're going to get with this kind of thing, and there's a lot of different cases you have to be careful with. But if you do that, make sure that your model's not overgeneralizing. You do a lot of good qualitative review, and incorporate additional logic, additional heuristics and metrics, and user input. You have a lot of power to categorize and group your failures in very, very interesting ways. And it's a very flexible system, which is really, really nice, right? Not everybody wants their failures grouped in the same way. Some people have different workflows. Some people have different jobs. Even organizations sort of, might want to group or categorize failures in unique ways. And so by having this sort of atomic units of these vector representations that can then be aggregated, you can do a lot of things. And you can do a lot of things in a lot of different ways. I will pass off to Luke for the conclusion.
Yeah, thanks, Justin. So where are we going with this next? After doing this initial work on ways to extract and analyze and kind of automate that analysis process, or the bones of it, looking into where does the human fit into this process? We're still, as we said before, that expert knowledge is sort of key to it. So ergonomically, where does the system where does the user interact with the system to provide input, to provide some guidance on how to classify certain things? What does that workflow look like? Also looking at how we can possibly detect and suggest remediation. So as like the example I gave before, something happened, a failure happened, then later a user took an action. Can we suggest if that same kind of thing happens later to perform the same action to fix it? Continue to look at different mechanisms for generating embeddings and evaluate those. Also expand our training and data set. So if you are a Develocity user and this sounds interesting to you and you're interested in kind of partnering with us and helping out, we're accepting data donations, I guess if I can put it that way. So come and talk to us about that. Yeah, and ultimately work towards having this available in Develocity as a first-class feature as we go along that path. So I think we're out of time. Thank you. If you have any questions, as Julianne mentioned, I'll be at the end. Thank you.
Thanks.